Welcome to Selection with Sathi. Today we master Dijkstra's algorithm, the most important single-source shortest path algorithm for weighted graphs. We will trace it step by step with code, understand edge relaxation, priority queues, and see when it works and when it fails. This is a must-know for GATE CSE and coding interviews. Let us begin. Let us start with the complete Dijkstra algorithm. Look at lines 4 and 5, initialize all distances to infinity, source distance to 0. Line 6, push the source with distance 0 into a min-heap. Line 8, pop the node with smallest distance from the heap. Lines 9 and 10, this is important. If the popped distance is greater than the current best distance for this node, it is a stale entry. Skip it. Lines 11 through 14, for each neighbor, check if going through the current node gives a shorter path. If yes, update the distance and push to the heap. This is the greedy approach. Once a node is popped with its minimum distance, that distance is finalized. The priority queue is the engine of Dijkstra's algorithm. We use Python's heapqueue module which provides a min-heap. Look at lines 5 through 7. We push tuples of distance and node name. The heap automatically orders by the first element, which is the distance. Line 9. Heappop gives us the entry with the smallest distance. Both push and pop operations take O of log n time. The greedy insight, when we pop a node, its distance is already the shortest. Why? Because all shorter paths have already been processed. Stale entries are handled lazily. When we pop a distance larger than the current best, we simply skip it. Edge relaxation is the core operation. Look at line 2. For each neighbor v of the current node u with edge weight w, line 3, compute the new distance as district of u plus w, line 4. If this new distance is less than the current district of v, we found a shorter path. Line 5, update district of v to the new shorter distance. Line 6, record u as the parent of v. This is for path reconstruction later. Line 7, push the new distance and v into the priority queue. Relaxation happens at most e times total across all nodes. Each relaxation involves one heap push, giving O of E log V total. Let us analyze the time complexity carefully. Each vertex is extracted from the heap at most once when it is finalized. That gives V heap pops, each O of log V total, O of V log V. Each edge triggers at most one relaxation, which is one heap push. That gives E heap pushes, each O of log V total, O of E log V combined, O of V plus E times log V. With a Fibonacci heap, the push becomes O of 1 amortized, giving O of V log V plus E. But Fibonacci heaps are rarely used in practice. For dense graphs where E is close to V squared, a simple O of V squared algorithm with adjacency matrix can be faster. How does Dijkstra compare with BFS and Bellman-Ford? BFS works for unweighted graphs. All edges have weight 1. BFS uses a simple queue and runs in O of V plus E. Dijkstra generalizes BFS to handle different positive weights by using a priority queue instead of a regular queue. Bellman-Ford handles negative edge weights by relaxing all edges V minus 1 times. It runs in O of V times E, slower but more general. The critical point, Dijkstra fails with negative edges. Its greedy assumption that a finalized node has the shortest distance breaks when a negative edge could later provide a shorter path.
Let us trace Dijkstra on a 5-node graph. Source is node 0. Edges 0 to 1 weight 4, 0 to 2 weight 1, to 2 1 weight 2, 1 to 3 weight 1, to 2 3 weight 5, 3 to 4 weight 3. Initialize district is 0, infinity, 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 infinity. Push 0, 0 to heap. Pop node 0 with distance 0. Relax edges, district of 1 becomes 4, district of 2 becomes 1. Pop node 2 with distance 1, the smallest. Relax, district of 1 becomes min of 4 and 1 plus 2 equals 3. Update to 3. Also district of 3 becomes 1 plus 5 equals 6. Pop node 1 with distance 3. Relax, district of 3 becomes min of 6 and 3 plus 1 equals 4. Update to 4. Pop node 3 with distance 4. Relax, district of 4 becomes 4 plus 3 equals 7. Pop node 4 with distance 7. Done. Final distances 0, 3, 1, 4, 7. Notice node 1 got distance 3 through node 2, not the direct edge of 4. Why does Dijkstra fail with negative edges? Consider 3 nodes. Edge 0 to 1 weight 1, 0 to 2 weight 5, 1 to 2 weight minus 4. The true shortest path to node 2 is 0 to 1 to 2, cost 1 plus minus 4 equals minus 3. But in some implementations without lazy deletion, Dijkstra would finalize node 2 at distance 5 when it pops from the heap before processing the path through node 1. With Python heap queue and lazy deletion, it may actually get the right answer here because the minus 3 entry gets pushed and popped before the stale 5. But the greedy guarantee is broken. In general graphs with negative edges, Dijkstra can give wrong results. Always use Bellman-Ford for negative edges. Let us understand the finalization order and why it guarantees correctness. Step 1. Node 0 is finalized with distance 0. It is the source. Step 2. Node 2 is finalized with distance 1. Why? Because 1 is the smallest distance in the heap, and no future path can be shorter since all edges are non-negative. Step 3. Node 1 is finalized with distance 3. The path 0 to 2 to 1 costs 3, which is better than the direct edge 0 to 1 costing 4. Step 4. Node 3 is finalized with distance 4. Through path 0, 2, 1, 3. Step 5. Node 4 is finalized with distance 7. The key insight, at each step, the smallest distance in the heap is guaranteed to be final. Now let us reconstruct the actual shortest path, not just the distance. During Dijkstra, whenever we relax an edge from U to V, we set parent of V to U at line 12 in the code. After Dijkstra finishes, the parent array is -1, 2, 0, 1, 3. To find the path from 2000 to 4, start at node 4. Parent of 4 is 3. Parent of 3 is 1. Parent of 1 is 2. Parent of 2 is 0. Parent of 0 is -1, stop. We traced 4, 3, 1, 2, 0, reverse it, 0, 2, 1, 3, 4, that is the shortest path with total cost 7. This parent array technique works for any single source shortest path algorithm.
Quick exam tips. First, Dijkstra only works with non-negative edge weights. If there are negative edges, use Bellman-Ford. Second, use a min-heap for O of V plus E log V. Never use a sorted list or linear scan in an interview. Third, for dense graphs where E approaches V squared, the simple O of V squared matrix scan can beat the heap approach. Fourth, Gate loves asking you to trace Dijkstra. Given a weighted graph, find the shortest distance and the actual path from source. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.